Okay, so we're saying Q implies P follows from not Q or P provided, and here just P. So we have that weakening rule that says whenever you have P, you also have P or anything else. So this is weakening. You'll see it in the homework or assignment as well. Right? Useful 376 laws. And this is just definition of implication. Right? Oh, somebody says recording has stopped, but as far as I can tell, recording has not. So I don't know. On my side, it said recording is still going. So I hope it is. If not, we'll find out later on, I guess. So no, notice now I'm starting with something and I can work my way back to find another result, right? In fact, I can use 4.1 directly. I don't even have to do the full proof. I can just say we're right here, and we can just say, oh, we have access to 4.1, which says if you know something is true, then you can weaken it by putting something else in front. So I can just put 4.1 directly. Right. No, I don't have access to theorem 4.1. Not in my current notebook, apparently. Theorem 4.1, P implies Q implies P, proof. So this is a good time to show you another proof. So you can say by, and then you can say I'm going to do shunting, and then I'm going to do weakening, right? So when a proof is really, really tiny, you can just put the proof steps together. You can say by, and then write the proof steps, right? So when the proof is really tiny, you can just write the word by instead of having to write a full proof. And you'll get to practice that in the upcoming assignment, which has a lot of tiny proofs. And then you can just write by if you want, right? All right, recording is working. Thank you for confirming. Yeah. So this is all. So this is just what by does. If anyone has questions, please let me know. Maybe I'll just make that clear. If your proof is I have step one, and then I have reason one, and then you have more steps, and then you have reason n, and you want to say p sub n. All right, and you're doing a theorem, for example, P1 equals Pn, and this is your proof. Then what you can do is you can say, hey, theorem P1 equals Pn, proof by R1, comma, R slash sub n. Okay, same as. All right. So whenever you have a proof like this for small n, okay. So when you have a small n, you can take a proof of this shape. If n is not too big, maybe 3 or 4, then you can try doing it like this. If it's more than 4, I recommend you don't do this. Otherwise, you don't know what's going on, and then there'll be a denial of service attack, and then you might lose marks. Academic dishonesty and all that. Okay, ducks. So this is how by works. How by works. Okay. Alrighty. Let's move on a little bit more. So when you don't have access to the reverse of these orders, right? Then you'll have to mention them explicitly. All right. So right here, we mentioned it explicitly. Okay. So just as we have automatic associativity and automatic symmetry, and sometimes we turn those off, we have this converse property. If we don't tell CalcCheck, hey, provided is the converse of implication, then it won't know what's going on here. It won't know that it's the converse, and you have to explicitly invoke it yourself. Okay, so just wanted to let you know about that. So there are some features that we might turn off, and then you will be expected to know how to do it without this relaxed proof style. So going forward in the next coming weeks, you should be able to do proofs using Chapter 4 relaxed proof style and without Chapter 4. Some proofs without chapter 4 will get really long, like really wide and really long, and it'll be very difficult to read them as well. So using chapter 4 is a really good idea, the relaxed proof style. Okay, so some of you might have already seen long and wide proofs, and without chapter 4, we're going to do more and more advanced mathematics. And if you don't use chapter 4, some things will just be very difficult to read. And there are some hints in the upcoming assignment on, strongly suggested you do chapter 4 relaxed style. Otherwise, life could be very, very difficult in progressing. Okay. So I recommend these 376. Definitely the first two. Definitely be able to prove the first two. And besides proving the first two, you should definitely know the first two. Everything is at most its maximum, and everything is at least its minimum, right? If you have two things, then the maximum of those is going to be at least either one of them. And if you have two things, the minimum of them is going to be at most either of them. Okay, if you think of and or as max and min. And to justify why you can think of and as minimum and or as maximum, assignment 2 is going to try to justify that. And then you'll be like, whoa, everything's the same. Right? It wasn't a weird correspondence. They really are very familiar. So I hope you're excited. And if you're not, let me know. So here's a theorem, left monotonicity of or, and left monotonicity of and. These are not too difficult to prove. And the idea is, we talked about monotonicity. Monotonicity is about inclusions for inclusions, all right? So an implication is an inclusion, all right? And P implies Q means P is included in Q. And I have an expression here, P or R, the maximum of P and R, all right? And we're going to say this is also included in the maximum of Q and R. So the monotonicity law is a proof that or takes inclusions to inclusions. This is a property of or. All right. Leibniz was about everything, but monotonicity is not everything. Some stuff does not admit monotonicity. Okay. So it's a very simple proof. I recommend you try to prove these yourself. They are in the book, so I won't take too much. I won't spend too much time on them. But they do justify some of the stuff we can do. For instance, if I have access to P or R, right, and I know P implies Q, then I can simplify only the P part to get to Q or R. So I'm only simplifying one part. So let's see an idea of this. Okay. So here's our theorem. Let's do P implies Q, implies P lower R, implies Q lower R. Proof. I don't think I have it beside me, so maybe I should check. No, I do have 4.2. Okay, good. So we have 4.2. So let's try proving this using the extended. So even though it's already proven, just to show you how it will work. So let's assume, assuming we have P implies Q. Okay. Now we'll say P or R and then we'll try to get to Q or R. So notice the shape of the calculation, right? We assumed some stuff, and now what we have to prove is easier. Now we only have to prove this thing. And this is very similar to an equality. Remember when we said if you have an equation, you try to show left-hand side equals right-hand side. So we start with the left-hand side, P or R, but notice it's not an equality anymore. It's an implication. So here we say implies Q or R. Okay. So you can try doing this. All right. Oh. All right. So we can just put the assumption right there, and notice it found the assumption, but it can't justify it. All right. So yes, we have P implies Q right here, but we're inside a context. We're inside P or R and Q or R. Okay, so to go inside of a context, you have to make use of monotonicity of or itself. Okay, so we can say we're using monotonicity of or with this assumption. Okay, so recall how with works. With just is essentially modus ponens, right? You have a theorem. We have this theorem. P or Q implies P or R implies Q or R. And when we use the word with, we're just saying, I don't want this part anymore, right? Like I've given you that part. So just give me this theorem, okay? So P or R implies Q or R, which is what we have right here, okay? So this is a common misstep in some students' proofs where they forget about the monotonicity. They'll just say, oh, I have the assumption and I'm good to go. But you need the assumption tacked on to the monotonicity, okay? So just as you use axiom replacement, 384, likewise with monotonicity, you have to make it clear that you're using monotonicity. Okay, next. All right, all good. All right. So here's another example. It's similar to one we've seen already, so I won't type it up. If you want me to show you any particular examples, please let me know. All right. So we already talked a bit about assuming. So just a bit more on this. When you assume P, you assume a part. So right here we assume P implies Q. We consider it a constant, like the number 5, right? So this P is like the number 5, Q is like the number 6. They're like numbers, and numbers cannot be instantiated. You cannot say, oh, let me substitute some things or use Leibniz on it to rewrite this Q into another P. Okay, so when you make an assuming, you're essentially saying, oh, we have true as a constant, we have false as a constant. Now we have two new constants called P and Q, and they're local to this proof. So they're only constants right here. Okay, so you have to treat them as if you're treating true or false or 0, 1, 2, right? You know, they're not things you can pick. They no longer become variables. You've taken them out of the status of variable to a higher status as being constants. Okay, so that's the main caveat. So unfortunately, some students say, oh, let me try to replace this Q with P or true. Just as with induction, in the induction hypothesis, you have that as a constant claim. You don't get to change the variables. Okay, ducks? All right. So you've seen this theorem before a few times. We've mentioned it, but we haven't really used it. And the reason we haven't used it is because we needed the keyword with to actually make use of cancellation. All right. Yes. So yes, this I used monotonicity to prove monotonicity here, but that was just to show you the proof style of how you can use it itself. So I just didn't have a clever example. I just put it in there. But for example, here I'll put Q land I don't know, D. Okay, P or Q and D. Q and D. All right, so it's not a great theorem, but just to show you what we can do. All right. Okay, so not too much fun stuff. There it is. And let's even make it even more fun. Let's go all the way to Q. All right. So here it is. Just somebody didn't like that example. Absorption. We can get all the way to Q. Okay. So we use monotonicity to show that if you have P, or Q and D, then you can just get Q. All right. Yeah, you're welcome. Yeah. My bad for not using a more interesting example. So here's an example over here on using with, right? So we've already talked about using with before, so I won't spend too much time on it. If you have questions, let me know. And I think we just used it a moment ago, so we'll not dwell too much on this. The cool thing about with is, remember how I showed you by a moment ago, right? So we talked about by. You can take a with and you can turn it into a subproof. Okay, so a subproof is like doing a proof right in the middle of a step. All right. All right. So another way to say it is you can expand it even further and say, oh, wait a minute, here is my subproof. Okay, so we can do that too right here for our little example. We can say, instead of doing it like this, Command V, and all Command C, Command V. Let's repeat this example, but this time let's not do with, let's do a subproof. So we'll say, all right, what we're trying to show is we want a theorem. So subproof for P or Q and D implies Q. This is what I would like a theorem for. Okay. Okay. So we're doing a proof right in the middle of our calculation, right? And here's CalcCheck acknowledging what we're trying to do, right? And we're not going to use monotonicity of OR directly with. So we'll say, all right, this is my goal right here, Command C. So here is my goal, and here is what I will do with my goal. First thing I'll do is I'll introduce true. All right, and then I'll copy that down. Boop. And I can introduce true because of the left identity of implication. Then what I'll do is I'll say, all right, now I have an assumption. My assumption is that P implies Q. So I can replace true with this assumption of mine. Command C, Command V. So this is now P implies Q. Okay. And what I'll do, I wanted Q or Q land D. Sorry about that. I forgot this extra part. Command V, Command V. So this is what we want. But wait a minute. This is just monotonicity of OR. Boop. Okay. So we just proved the theorem right in the middle of our. Ooh. Seem to have, sorry about that. Got to indent all the way as usual. Okay. Okay. So right here, that part was missing. So we just proved what we needed to make our step go through. So if you're not comfortable using with, you can just do the subproof in place. I don't recommend that because this is a lot of work, right? First, we have to be clever and find there's a left identity. Then we have to invoke our assumption. Then we actually use the main theorem. So using with essentially saves us all this typing. We just call on our assumption using monotonicity. That's all. Okay, next. All right. So you can, and of course the book shows you in chapter 4 that all of these relaxed proof styles you can always get rid of them. You don't have to use these relaxed proof styles. They can always be expanded away into. Okay. Unfortunately, you might not want to use a longer calculation, and that's the point of the relaxed proof style. It can make some things easier for you. Okay. More readable, as it were. Okay, ducks. So here is a shorter proof of the monotonicity of and, right? And we're just using weakening this time. We drop the P. That's all. Okay. So let's do that again. This time, let's not be so hasty. So let's show this theorem, but for monotonicity of OR. So this time, somebody was upset that I used monotonicity to prove monotonicity. This time, let's not do that. So let's start here. Boop. Now, let's actually change this to R implies Q implies R. Okay. So let's try to show that P or R implies Q or R. If something is before an implication, so I have this stuff implies some other things, then everything before the implies you can put as an assuming clause. Okay, so that's how assuming works. So we assume everything that's before the implication right here. So all this is before the implication on the second line. Okay, so we assume that right here. Now let's try to show P or R. Now, some of you might remember P implies Q is the same thing as P or Q equivales Q, right? So you might want to say, oh, this is P or Q, right? I want to make use of that theorem. P or Q equivales Q, right? So you might want to say, since P implies Q, P and Q, sorry, P equivales P or Q. You want to do that somehow, and then you want to put R in there, right? So you can try to do that, for example. Okay. So how would we do it is the interesting question. How do we actually get this? I'm just looking at the questions here. Are we all good? We're all good? Okay. Okay. So I have P or R, and oh, sorry, yes, that was a typo. And we want to get the Q or R, right? So how would we do it, right? So let me show you. What you do is you use this thing called and using with. So in this particular place, actually, it would be much easier to show you this theorem. This theorem might be much easier. Sorry about that. Yeah, I had that wrong anyways. Okay. So we want to use this. We want to use P implies Q in this shape, right? To get it like this, and then we can just do weakening. Ooh, weakening, right? And we drop the P to get just Q and R. Okay. But how do we make this formal? What do we do here? Well, we want P implies Q, and we want to replace. And we know that implication is the same as P equivales P and Q. So how do we get it in this shape? So we'll say, assuming P implies Q, and we're using definition of implication. Okay. And so now I can just say our assumption that P implies Q. Okay. So let me try. Oh, I seem to. Sorry. And using with. So remember we talked about how with can rewrite parts for you. So we say and I'm using with. I'm using the with combinator here so that I can treat P implies Q as if it was P equivales P and Q. So now when I call on my assumption, because I'm using definition of implication, my assumption P implies Q actually refers to this alternate form. Okay, dokes? So I hope that makes it clear. And I did try to put a using with question for you on the upcoming assignment. So places to practice. Okay, dokes. So this is one way to use it. You can take this idea of I have an assumption and I know my assumption is equivalent to something else, and to make this equivalence you use using with. All right, and that's what we have here as well. Right, using with. Okay, dokes. Are there any questions, concerns, or queries before we move on? Okay. So next we'll just look at some proof techniques. So we talked about fold, unfold, right? We talked about when you're showing an equation, start with the more complicated side and simplify. Right? So we have two main ones. Then we got to induction. Induction is about working with the natural numbers, right? If you want to show a property is true for this infinite collection 0, 1, 2, 3, you use induction, okay? Here is another pattern. Sometimes you want to show a statement S is true, and you don't know how to do it directly, but you know, hey, if I know P was true, then I can show S. If I know Q was true, I can get S, and if I know R was true, I can get S. So you don't know how to prove S directly, but you're saying if P was true, I know how to get S. If Q was true, I know how to get S. If R was true, I know how to get S. So if one of these scenarios, in each one of these scenarios, I know how to get S. Okay, so that's what this bottom box says. In one of these scenarios, in each of them, I know how to get S. Now, do any of these scenarios actually happen? And that's what we say by the idea that it's complete. Right? We call it completeness. Right? It means one of these scenarios will happen. So quoting Shakespeare, to be or not to be. Right? So when B does happen, I can do things. And when not to be happens, I can do other things. And I always know by the law of the excluded middle that to be or not to be is always going to happen. One or the other is always going to happen. Okay. So this is the idea of case analysis. All right. So here is a proof right here, just to show you. We want to show that m minus 0 is equal to m. We don't know how to show that directly for all m, but we say, oh, when m is 0, I know what to do. I can show my proof. And when m is the successor of another number, I can show this proof. Okay. So this is important. This is one m. This is a different m. So maybe I should have called it n. All right. So this is called. They belong in different namespaces. That's why I'm using two different. That's why m being used on different sides of the equality is okay. But that should have been an n. Apologies. Okay. But in this case, I know how to show it. In this case, I know how to show it. All right. But do either of these cases happen? Well, we have a theorem right here that says yes. Every number is either 0 or the successor of the predecessor of n. Right? No, sorry, I was right about this. Yeah. If I minus a number and then I add the successor to it, then I know that number is going to be itself again. Successor and predecessor are inverse operations. Okay. So I can show the theorem in one scenario. I can show the theorem in another scenario, and I know that I always have one of these scenarios. Okay. So let's try proving a theorem, because it's always fun to try to prove theorems, except when I fail, because then I will be upset. So let's assume. So somebody asked earlier if we can have multiple assuming clauses. So let's assume P implies R, and let's assume not P also implies R. Then with these two guys together, we can get R. Right? Does that sound reasonable? Let's read it. When I have P, I can get R. And when I don't have P, I can always get R. So 2P or not 2P, I always have R. Okay? So let's try to prove it. Please, God in heaven, let this work. So here's our proof. Let's do by cases. We're going to do two cases. We're going to case on P, and we're going to case on the negation of P. Okay? And then we're going to have a proof when P is true, how do I get R? And we're going to have a proof when not P is true, how do I get R? Okay. Oh, and I forgot completeness. All right. Completeness. All right. No case proofs. All right, I'm apparently in a notebook. Oh, sorry, I forgot to make the assuming clause. Assuming P implies R and not P implies R. Sorry, I forgot to make my assuming. Okay, so we assume the stuff we know, and then we try to make some case clauses. Assumption matches goal, no case proofs. Yes, I don't have any case proofs. Let me put a case proof right here. Okay, let's see. V. All right, I have two case proofs. No, unexpected trailing block. No case proofs. Parse error. Bah. Trying to do things does not always. By the law of the excluded middle, we always have one case or the other. For case of P, I apologize. I don't know why I'm getting these errors. I will try to show it to you, but it's unfortunate that I'm getting these errors. So we have R, and we have an assumption that tells us P implies R, and so we can get R. Like slash provided P, and then we have another assumption, right, for our case, and from that one we can get R. Yeah. Cases are kind of just looking at scenarios, and it's kind of doing truth values. The example I'm showing you involves very simple proofs, proof expressions. So I'm just showing you for P and not P. I really am essentially doing scenarios. In this example, they're more complicated. Here, M is 0, and here M is the successor of the predecessor of M. Okay, so they can be more complicated. But I'm gonna stop because I can't get it to work, and I don't want to feel bad, so I'll just stop. All right. So I just want to show you a few more before we move on. So everything is positive or it's not positive. Excluded middle. You can do casing. Not a big concern. The other proof method I want to mention really quickly, because I'm running out of time, is proof by contrapositive. So you'll find these in any basic elementary proof book. To show P implies Q, just show not Q implies not P. Okay, and the way to do it is you just say, here's my proof, and I'm using contrapositive. Okay, so not a big concern. So you've seen mutual implication, you've seen contrapositive, all these theorems you've seen that say, hey, this thing is equivalent to this other thing. You can stick them in front of the word using, and now those theorems are themselves proof techniques. Okay, so now you can use any theorem that has an equivalence as a proof technique. Right. So here's contrapositive. To show this thing implies the other one, we start at the other one negated and show the negation of the first thing. Okay. Here's mutual implication, which just says to show two things are equivalent, just show one of them includes the other. Okay. So we say we're using mutual implication, and then we have a subproof for the first part and a subproof for the other part. Okay. So notice mutual implication has an and in there. Okay, to show two things are equivalent, show two pieces. All right. Let me just finish up, and then if we have time, I'll do some more. Proof by contradiction says to show not P, just show P implies false. Okay. This is far too popular. A lot of people like to use this, and they don't always have to. So let's just look at a quick theorem. Let's show that it is not the case that 0 equals 1. Okay, that's a great theorem, isn't it? So here's how do we prove that 0 is not equal to 1? All right. We will say using 4.9. So that's the theorem we'll try to use, all right, which says to show a negation, you just show the other one. So now we need a subproof for 0 equals 1 implies false. We need a subproof for that. Okay. So we'll start off with 0 equals 1. We'll go here. This implies, I'll just cheat and use a fact. 0 equals 1. Don't judge me, guys. Don't judge me. It's hard to do stuff on the fly. All right. It's not a great example, but I tried. This is like that. Well, what's wrong? Could not justify this step. Oh, there's a theorem called 0 is not successor. Oh, that's a different. We're all in different setups, guys. Evaluate. Let me try to evaluate my way out of this. All right, I can evaluate my way out of this, and then I will do something silly, and then I can say this is false. Reflexivity of this guy. Bah. All right. Okay. So this is a very, very silly theorem. Could not resolve theorem reference 4.9. I don't even have 4.9 in scope. But yes. So it's a very silly little proof. I need double negation somewhere. Somebody says I need double. Oh, okay. Sorry. L naught, L naught. And this is why a lot of people don't like to do live coding, because you can mess up and then you look bad, and people feel bad when they look bad, and you know. All right. So come on. All right, we were so close. We did not succeed, but that's life. I will continue to play in this playground because it makes you guys feel better. It makes me feel silly because sometimes I know what I'm doing, but I type silly things. Anyhow, I hope you all had a fantastic Friday. I wish you all the best with life. Have a great reading week. There is a midterm 2 makeup happening super soon. Like, tell me now if you need to make up your midterm. Otherwise, you'll miss the makeup. Please send an email to me and Professor Wolfram Call. CC both of us. Bye. Or I'll be here to continue chatting if you want. But maybe if stay here and chat too if you'd like. But I'll stop recording right now. Bye.